Okay, so we're going to start day 1 review for AP2 for the fall. And we're starting with fluids. If you remember way back with fluids, it was a fairly simple chapter, but we need a review for it. So the first concept was density, which you may have learned in chemistry or even in some general science class. And density is in fluids is like inertia, right? Like mass for fluids. Density is simply mass divided by volume. And so density, which is rho, right, this symbol here, rho, is equal to m over v. So lots of times we simply replace our m in our equations with rho v, right? Specific gravity is the ratio of the substance density to water density. So it's just a way to kind of compare it to water. So if the specific gravity is greater than 1, right? If it's greater than 1, it sinks, and if it's less than 1, it floats. So it's just a way to be. So if you know the specific gravity is 0.75, you know that the density of the substance is 75% of water, so it'd be 750 grams per milliliter instead of the 1,000 that we normally see for water. Pressure is another concept that we covered, and pressure is force per area. So P is equal to F over A. The units are Pascal. It's got to be in newtons and meters. You don't need to memorize these numbers right here. Those are on your table of information. It does tell you that 1 times 10 to the 5th pascals is equal to 1 atmosphere is equal to 760 torr. It's equal to 760 milligrams. It may not have the torr, but it definitely has. It may not have this one, but it has the 760 milligrams of mercury. Remember, that's also the same as 100 kilopascals, so you'll see that sometimes. And you need to remember especially that pressure is a scalar, and so it's perpendicular to the surface. So it doesn't matter how much stuff you have, it just matters how high up it goes, right? So that comes with the next equation. So when we're looking at pressure of a liquid, the pressure of the liquid above the object is only due to the height, right? It's directly proportional to H. So the important thing to understand here is that H is the important factor, right? This H. So rho GH tells you what the pressure of the liquid is. Oh, that looks like a little p, but that's a big P. That's the pressure of the liquid. And you can add it. It's additive, right? So if you see here, the P total is the P of the liquid plus the P of the air, so it's rho GH plus P atmosphere. Gauge pressure, on the other hand, you take out the atmospheric pressure, so it's a little bit less. So P gauge is always less than P total, and P gauge is the one that's rho gauge. So you always have to read the problem carefully, because I know I mess that up all the time. So once you think you've got it, read it again, make sure you've got it right. But remember, H is what's the most important thing, not the volume, not how much you have, but just the H. So if you graphed pressure versus depth, you get a direct relationship since it's directly related to H, and you notice that the gauge pressure is below the total pressure and starts at 0, where gauge pressure or total pressure starts at atmospheric pressure, because we're including that. Buoyancies, submerged block only has a net force in the vertical direction because all the other forces cancel, and the net upward force is known as buoyancy. So if we're doing a free body diagram of an object that's sitting in water, we know we're going to have FG going down and FB going up. If it's floating, they're going to be equal. If it's not floating, then they still go in those directions. It's just they're not equal anymore. The buoyant force is always equal to rho VG, and you have to remember which rho we're talking about. Remember, that was where the confusion came from. So we know rho V is mass, so this is really mg, the weight of the fluid displaced, right? So sometimes you guys get all confused because it says you displaced 100 kilograms of water. Well, then just multiply it by 10, and you know the weight, and you know the buoyant force. You're done. You don't need to do anything else. So it's the liquid that's displaced, the fluid that's displaced, the air that's displaced, whatever it is that we care about. It's the weight of the fluid displaced. That's the concept, the weight of the fluid displaced. So if I displace more fluid, then I get more buoyant force. The submerged part is only the volume submerged or displaced, right? So it's not the whole volume of the object, right? When you put in there, it's only the part that's underwater. So if I have something like this and I have a raft or something in there, then I only care about this part when I'm finding the volume, and it's just that volume, not the whole volume of the whole thing. If it says FB equals mg of object, since the net force is 0, this is only if it floats, right? If it's not floating, that's not true, right? Because then it sinks, because you could have two forces, right? I could have this object, and it could sink down to the bottom, and the water's up here, and I still have FB, and I still have FG, but they are no longer equal. But now you have this thing called apparent weight, and you can subtract to figure out what the apparent weight was, and what you would read, but it's definitely not equal. So make sure you realize that it's only if it floats that FB is equal to mg of the object. So if you look at the ratios, right, you can use this ratio concept to be able to figure out what the density of the fluid is, right? So if the whole thing's submerged, right, then you have a ratio of 1, then that means that the rows densities are 1, they're going to be equal. So the more I have, the more as the V sub submerged goes up, that means that the row of the object goes up, right? That makes sense because you got to displace more concepts. Don't worry so much about the math. So the ratio of densities is the ratio of how much is submerged. Flow rate. So remember, when we're looking at flow rate, you got to be careful of what kind of flow rate. So in this case, if we looked at the units of A times V, that would be meters cubed per second. So this is what we'd call volume flow rate, right? So be careful of which kind of flow rate we're talking about, because it could be mass flow rate, which is definitely not meters cubed, right? So just pay attention to what it says. But this equation, we're looking at flow rate, which is also known as Q. I know, not to confuse it with heat. And remember, flow rate is not the speed, because the V here is speed, right? So don't confuse speed. Don't confuse which kind of flow rate you have. So the flow rate is the amount of fluid per time. The flow rate is how fast the fluid is actually moving. The big concept is that if you have a narrow pipe, it goes faster, because if A goes down, V goes up. V goes up. The speed changes inversely proportional to the diameter squared. Remember, you can be diameter or radius. It doesn't matter because they're the same thing. So if the diameter of the pipe changes from 8 to 2 meters, and the speed changes from 2 meters per second, and it got narrow, so it's going to go faster by 4 squared, so it's going to be 32 meters per second. So Bernoulli's equation is super important. So Bernoulli's equation is a statement of conservation of energy. Well, it's not perfectly true for our class. It works. It's for an ideal fluid, so you have to have an ideal fluid with low viscosity. You have to have low viscosity, and you need to make sure that it's not, running all over the place. It's just basically streaming through. And so if you just look, this becomes constant. So the pressure plus the rho Gy, which is like our potential energy, plus the 1/2 rho G V squared, which is like the kinetic energy, stays constant, right? This whole thing stays constant. And so if you keep the pressure the same, right, if this P and this P are the same, then we can ignore those two P's, and then you can, and let's say, you have your tube or something like Torricelli's, then you end up with, at the top, it's basically not moving either, and the pressures are the same on both sides, and then it's not got any height, so you end up So with Torricelli's theorem, and you have things open at both sides, you simply end up with rho Gy equals 1/2 rho V squared, right? And then you can cancel out the rows, and when you solve it, you end up with V equals the square root of 2GH. Just remember, you cannot just start here, right? You have to explain how you get there if you use that theorem. And so that but you do see that the speed at the efflux speed at the bottom of the hole is going to be proportional to the distance h of the water above it. Remember, so if I have a container and there's a hole and the water is filled here and the water is coming out, this is the top of the water. This is h, right? Not the whole thing, just to the top of the water, because that's what's causing the pressure that's making it go down. The Bernoulli effect is just the idea that when you're using this equation up here, that if you have the pressure go down, especially if it's going in a straight line like this, right? If the pressure goes down, the velocity goes up. I guess usually it's the other way, right? The velocity goes up, so the pressure goes down. But they are inversely related, which explains why balls curve and tennis balls drop and motorcycle jackets puff out and blah, 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 all those kinds of things. So let's look at a sample problem. So we have a swimming pool and it has a depth of 4 meters. What is the hydrostatic gauge pressure at a point 1 meter below the surface? So we've got the swimming pool, right? Here's my swimming, oops, that's a funny looking swimming pool. There's my swimming pool. And we're 1 meter below. We want to know what the pressure is. So my pressure is equal to rho GH, and I know the only H that matters is the 1 meter. So it's going to be equal to 1 times 10 to the third kilograms per meter cubed, because that's the density of water, times 10 meters per second squared, times 1 meter. That's not so bad, right? 10 to the third times 10. So it's like 1 times 10 to the fourth pascals. But the concept is, this is like a multiple choice type of question. The concept is that the 4 meters isn't important. What's important is the 1 meters when you're looking at pressure. Another problem, a helium balloon has a volume of 0.03 meters cubed. What is the net force on the balloon if it's surrounded by air? And so, again, we've got to figure out which things I want to do. So here's my balloon. We know there's 2 forces on it. There is FB and there's FG. We know that FG is going to be equal to mg of the balloon, which is the helium. And so we know that's going to be equal to rho Vg of the balloon, whereas Fb, well, it's equal to rho Vg. They're different rhos and different Vs. When I'm dealing with this first one, it's going to be the rho of the helium, so it's going to be 0.2, so it'll be 0.2. I'm going to skip just because of space units. Don't do that. It's not a good idea. And then the volume is the total volume, so it's 0.03 times 10, right? So that's like 0.6, I think, maybe. And then newtons, because 10, that's 0.3. What was that? 0.06. That's 0.06. You guys are better at math at that part than I am. And then let me just double check, just so I feel better. So 0.3 times 0.2. Yes, it's 0.06. And then for the buoyant force is going to be equal to the other density, right? So it's going to be the density of air because that's the fluid displaced. So that's 1.2. Still the volume because that's what's being displaced. So 0.03 and then times 10. So that's going to be 0.3 times 1.2, which is 0.36, which equals 0.36. So that means the sum of the forces is going to be FB minus FG, and so it's going to be 0.36 minus 0.06, yes, which is equal to 0.3 newtons. So it's going to float, yay, because it's a helium balloon. Good job. And then this one, the side of an above-ground pool is punctured and water gushes out through the hole. So we've got a pool, and there's water. The total depth, I guess there's water throughout the whole pool. The whole thing is 2.5 meters, but the puncture's right here at 1 meter. So I only care about this h, which is going to be 2.5 minus 1, which is equal to 1.5 meters. So that means that according to Bernoulli's equation, right, let's start from the beginning and not just jump to the theorem, right? We know P is equal, P plus rho Gy plus 1/2 rho V squared is going to be equal to P plus rho Gy plus 1/2 rho V squared. But we know that the pressures are the same at the top and the bottom. We know that it's not moving at the top and there's no distance at the bottom. So now I'm left with rho gy equals 1/2 rho v squared. I can cross off my rows. And now I can get to that equation that I already knew, which is the square root of 2gy, which is the square root of 2 times 10. What was my y? My y was 1.5 times 1.5. Pull out my trusty calculator, and we do 20 times 1.5, and really 20 times 1.5 is 30. Do that again, just make sure. 20 times 1.5, yeah, it's 30. All right, and then we're going to take the square root, which is this one, square root, which is 5.4. So it's like 5.5 or so, 5.5 meters per second. Done.